Okay, so continuation. We are saying when it gets to the bottom of this slope, we also have zero potential energy. Okay, so for the other part, make sure you refer to the other video. Okay, it was simply cut. Refer to the other video, the one starting with question 1, and then you can catch up from here. Okay, so we're saying at the bottom, this wheel has got zero potential energy, and it only remains with the kinetic energy, okay, which is translational kinetic energy as well as the rotational kinetic energy. Okay, so let's look at the equations. We have that potential energy at the top plus 0, meaning that kinetic energy is 0, is equal to 0 potential at the bottom plus the total kinetic at the bottom. Okay, so we have potential at the top plus 0 kinetic at the top equals 0 potential at the bottom plus total kinetic at the bottom. Okay, so at the top here we only have potential energy. We only have potential energy being equal to the total kinetic energy at the bottom, and we're having translational kinetic energy as well as rotational kinetic energy at the bottom. Okay, therefore we have that mgh equals half mv squared as our translational kinetic energy plus half I omega squared as our rotational kinetic energy. Okay, so let's call this equation 1. Okay, so we pause here. Now, radius of gyration. Okay, we know that the radius of gyration is given as k equals I over m, where I is simply the moment of the of inertia, and m is the mass of the rotating object. Okay, so from this equation of radius of gyration, we can find the moment of inertia being given as I equals mk squared. Okay, take note here that our k is the radius of gyration, so we have I equals mk squared. We can label this one as our equation star. Then also notice that omega, or rather angular speed, is given as the linear speed over the radius. So we have omega equals v over r. So if we square that, we're going to have omega squared equals v squared over r squared. And we can label this as our equation star star, okay, or double star. Yes, so if we substitute equation star and equation double star into equation 1, we are going to have our equation 1 as mgh equals half mv squared plus half m, or rather half I squared times omega squared. Okay, notice that I'm simply replacing where there was I, I'm putting mk squared, and where there was omega squared, I'm putting v squared over r squared. Therefore we have mgh equals half mv squared plus half mk squared times v squared over r. Okay, so we are looking for the linear speed here for v. Okay, so this simply makes our life easier. So notice also that the mass is simply going to cancel out on both sides. So we're going to remain with gh equals v squared over 2. Okay, v squared over 2 is common on the right side, so we simply factor it out. We have v squared over 2 multiplied by 1 plus k squared over r squared. Okay, again here, this is just mathematics here. You should try to work it out. In case you have any queries or questions, you can always reach out to me on Telegram. Okay, so here we are going to make v. Since we are looking for v, we have v squared equals 2gh over 1 plus k squared over r squared. Okay, we know g, we know k, we also know r, so our v squared is simply going to be 7.84 over 1.69. Okay, so we're simply substituting here the value of k, we know it's given, the value of r, it's given, we know what g is, we also know the height. Okay, 0.4, it's there. So we're simply dividing these two and we're getting v as the square root of 7.84 over 1.69. Therefore, our linear speed is 2.15 meters per second. Okay, so to find the angular speed, it's even easier now. We know that omega equals v over r. Okay, so in this case, it was supposed to be omega final equals v final over r. Okay, which is just the same thing anyway. So we know our v is 2.15 and our radius is 0.06 meters. Therefore, we get our v as 35.83 radians per second. Okay, but the question requires us to find this omega in revolutions per second. Therefore, we simply convert 35.83 radians per second to revolutions per second, and we're going to have 5.7 revolutions per second as our angular speed at the bottom. Okay, so this was quite easy. Just follow through the steps. Make sure where you are not clear, you can always ask. Okay, this is a video. If you're not clear, ask. I'll provide further explanation. Okay, so we move on to question 4. We can read. Okay, so question 4 here, we are going to deal with the conservation of angular momentum. So we have this disk which is rotating, okay, at a uniform, rather rotating at a speed of 15 revolutions per minute about an axis, and then some person simply jumps onto this disk, okay, sits down the edge, and we now want to find the new speed. Okay, so notice that this disk is moving with an initial speed, okay, and when this person jumps onto this rotating disk, the new speed is going to be for both the disk as well as the person who has jumped onto the disk. Okay, so they are going to be rotating at the same speed, so meaning that the final speed is going to be the same, because the person is simply going to sit on the edge of this disk. Okay, so this is more like a collision where we have object 1 hitting object 2, and then they skid together with the same speed. Okay, so we can relate that to this situation here. Okay, so we have object 1 as the disk with the mass of 150 kilograms, and our second object here is this person with the mass of 80 kilograms. Okay, so conservation of angular momentum gives summation of angular momentum before must equal to the sum of rather angular momentum after. Sorry. Okay, so before we proceed, we have to take note that the moment of inertia of a disk is going to be I disk equals half mr squared, okay, where m here is capital, okay, capital meaning the mass of the disk, and also the moment of inertia for this person is I naught equals mr squared. Notice that the m here is a small letter, meaning the mass of the person. Okay, so conservation of angular momentum therefore gives moment of inertia of the disk multiplied by the initial angular speed of the disk, okay, plus moment of inertia of the person multiplied by the initial angular speed of the person must equal to the finals of these. Okay, so we have id omega initial d plus I naught omega initial naught equals the finals of this, just like linear momentum, except in this case we are expressing it differently. We're using I and omega. Okay, so we know that the initial angular speed of a person is 0, okay, meaning that the initial momentum of this person is 0. So we remain with the angular momentum of the disk being equal to the final speed, because they will move with the same speed, multiplied by the moment of inertia of the disk plus moment of inertia of the person. Okay, I hope this is not confusing. So you can use yeah, well, make sure you are following through. It's just similar to linear momentum here. Okay, so now we can solve for the final speed of both the person and the disk as omega final equals initial angular momentum of the disk divided by the angular the moment of inertia of the disk plus moment of inertia of the person. Okay, so we can call this our equation 1. Okay, so now we know that we know the mass as well as the radius of the disk and also the mass of the person. So we can evaluate the moment of inertia for these two separately. So for the disk, we have mass of disk times the radius over 2, giving us the moment of inertia of the disk as 2700 kgs square meters. Okay, similarly we find the moment of inertia of for the person. We have I naught equals mass of the person times the radius, giving us 2880 kgs square meters. Okay, so with these values we simply substitute into equation 1 here. We substitute our id as well as I naught, okay, and we can simply find our final speed, or rather the speed with which the disk will be rotating, as 7.72 revolutions per minute. Okay, so when this person jumps onto this disk, the speed simply changes to, from 15 revolutions per minute to 7.26 revolutions per minute. Okay, so this is the final speed of this disk. Okay, so just follow through the steps here. It's simply conservation of angular momentum here. Okay, don't get confused, it's very simple. If you find the notation I'm using confusing, you can always use your own. Okay, so this was easier for me to identify the moment of inertia of the disk and the moment of inertia of the person, and also the speeds. Okay, so you can use your own notation, but make sure you are doing the correct thing. Okay, so we move on to question 5. Okay, so we have this system. Okay, the system is released from rest. Okay, so initially it's at rest, and we have a belt sort of passing running passing around the disk like that, and then we have two masses hang on both sides. So when we release this system, we expect the more massive object to go down and the one which is less massive to go up. Okay, so while this is happening, we are going to have this disk, or rather the wheel, is going to rotate. Okay, it's going to rotate, and now we want to find how fast it's going to rotate after the more massive object has fallen 2 meters. Okay, and we also want to know how long it takes for this mass to drop this far. All right, so here we can let our M1 mass 1 be equal to 0.52 kilogram, which is the more massive object here. Then M2 has 0.5 kilogram. And then also we can let the sum of these two masses be M3, which is going to be M3 equals M1 plus M2, giving us 1.02 kilograms. Okay, so now let us consider the conservation of energy for this system. Notice here that if we release this system, or we set it into motion, we are going to have the lighter mass gaining potential energy, and the more massive object rather is going to lose some potential energy because it's going downwards. Okay, so negative displacement there. And then at the same time, as both objects are moving, there's going to be a gain in kinetic energy for both. Okay, and there's also going to be some rotational kinetic energy for the wheel. Okay, so now let's consider the conservation of energy. We are saying that the change in potential energy is going to be the gain in kinetic energy here. Okay, so now we know that mass 1, which is the more massive object, is losing potential energy, therefore it's making a negative displacement. So we have mass 1 times g times negative h, because it's going downwards, plus m2 gh. Okay, so m2 is gaining potential energy, giving us the total kinetic energy for both objects. Okay, we have half m3 v squared, okay, plus the rotational kinetic energy of the wheel. Okay, so here we have gh. On the left hand side we have gh, which is common. Then we have m2 minus m1. Okay, so make sure you work this out. Make sure you work this out on your own. So we have gh m2 minus m1 equals half m3 omega squared r squared plus half I omega squared. Okay, so here on the right hand side I am saying half m3 omega squared r squared, because we know that v equals omega r. Okay, so if we square that, then we're going to have omega squared r squared. Okay, so now let's move on. We have gh therefore equals m1 minus m2. Okay, it's going to be m1 minus m2 being equal to omega squared over 2 multiplied by m3r squared plus I. Okay, so don't be confused here. Make sure you're following through. Where you're not clear, you're always free to ask. Okay, post your questions on Telegram, even on WhatsApp, it's okay. Okay, so from here we can find omega squared as 2 multiplied by m1 minus m2 times gh over m3 r squared plus I. Okay, so we know what m3 is. It's this mass of both objects. We know what I is, the moment of inertia of that wheel. So we simply substitute these values. We're getting, okay, substitute those values, and then we are going to get omega squared as 78.42. Okay, and then the square root of that gives us omega equals 8.86 radians per second. Okay, so we have found our omega here. It's just mathematics on this part. You don't get anything confused. Okay, so now we move on. What else are we finding? We also want to find how long it takes for this mass to drop this far. Okay, so we now want to find the time it takes for this mass to drop this far. Okay, so we have this equation of motion here. We are saying that x, or rather displacement, equals average speed times, or rather average velocity times the time, which is going to be v2 times the time. Okay, so if we let our x, or rather our displacement, be the height, which is 2 meters, okay, and we also let v be equal to omega r, then we can have our x, or our h, being equal to average angular speed multiplied by the time, from which we can find our time as 2 over 0.31, giving us 6.45 seconds.